Hello everyone, I am going to present our work on orchestrating virtualized core network migration in OpenROADM SDN enabled network. This is a joint work from UT Dallas, Scala Superior Antenna and IIT Dharwad. This slide shows the outline of the presentation. As we know, 5G mobile networks are able to support billions of devices with high data rates, more reliable, having almost no delay. These objectives can be achieved with the help of NFV and SDN concepts in the CRAN architecture. By exploiting both NFV and SDN, the radio network elements are implemented as virtualized network functions in order to simplify network programmability and reconfiguration. Here, VNFs run as software components on top of either virtual machine or container. Moreover, due to virtualization of core network components, fault-tolerant schemes need to be considered to recover the mobile application failures in order to maintain application quality of services. This slide shows the cloud-based architecture of the LTE core network exploited in our study, which is derived from the ETSI NFV standards. This study aims at integrating virtualized core network components with PRONET Orchestrator in order to meet the quality of service requirements during the link restoration. In our testbed, the PRONET Orchestrator from UT Dallas acts as NFV Orchestrator by supporting different virtualized infrastructure manager like OpenStack. Here, the VNF manager is responsible for deploying and monitoring the virtualized core network instances. NFVI resources such as compute, storage, and network are managed and controlled by VIMs. This slide shows the considered system model. As we know, the existing resiliency schemes allow to overcome the link failure by dynamically rerouting the packets. As shown here, initially the base stations are connected to the core network using the green link. However, due to the green link failure, the red paths are established. The dotted green lines show the migration of the core network components from Site C to Site B. In addition, we need to remember that, if the necessary channel capacity or latency is not achieved with the restored link, an additional complementing fault tolerance mechanisms may be required based on the core network component relocation. Moreover, besides maintaining the network connectivity, the considered migration solution must also continue to guarantee the quality of services. This slide shows when to perform the migration upon the link restoration process, as the desired link capacity may not always guarantee during the restoration process. As shown in the flow chart, the following steps are performed when the migration required. The link restoration process is initiated once the link failure occurs. If the restored link supports the required backhaul capacity demand, then UE communication service is restored. Otherwise, select the optimal migration approach. Upon selecting the migration approach, migrate the core network VNFs close to the edge user in order to restore the UE communication service. This slide shows the considered experimental testbed. All the RAN and core network components are deployed at UT Dallas testbed. This testbed is used to investigate kernel-based virtual machine for VM migration, and checkpoint restore in user space for Docker container migration. 2 racks of compute nodes are connected through optical transport consisting OpenROADM compliant equipment. The virtualized core network software components such as HSS, MME, and SP Gateway are first executed on the left rack, rack 1. Upon migration triggered, the core network components are migrated to Rack 2 over a dedicated optical circuit, light path. Here, the light path is dynamically created between the two racks to form a temporary high-speed connection in the management network to expedite the migration procedure between racks. This slide shows the considered three different performance metrics such as migration time, UE service recovery time, and impact of transport network propagation delay on the migration. The migration time is defined as the time involved in migrating a VNF from the source node to the destination node. The UE service recovery time is defined as the time interval during which UE connectivity is temporarily disconnected from the mobile network. Three different components such as MME, HSS, and SP gateway are considered for migration. This slide shows the type of migration techniques considered for VM and container migration. VM pre-copy method contains three different stages such as pre-live, live, and post-live migration stages during the VM migration. Whereas, container stop and copy method contains checkpoint, metadata transfer, and restoration stages for container migration. In order to get more details on each stage of migration, the interested readers can refer the below-cited publications. This slide shows the migration time as a function of three core network components. For all three core network components, VM migration time almost doubled that of the container migration, independent of the image flavor type. As we can observe that, the VM migration time is higher, due to the additional time required to transfer larger disk in terms of gigabytes, along with memory pages. Whereas, container migration time is lower because the measured container metadata size is in terms of megabytes only. Moreover, the HSS container migration time is higher when compared to MME and SP gateway. VM migration time has a noticeable difference due to flavor change. However, the container has an almost negligible difference in migration time specifically for MME and SP gateway components. This slide shows the UE service recovery time. Note that the UE service recovery time is measured in the data plane by monitoring the ICMP traffic between the UE and the GTP interface of the core network. As shown in figure, the red line shows the primary server response time, which is around 20 milliseconds when the UE is properly connected. However, upon link failure initiated, the UE service is interrupted for the duration of 2.3 seconds when container migration is considered, and 5.4 seconds when the VM migration is considered. Note that only UE traffic loss is observed, however, the UE still remains connected during the migration. This slide shows the MME migration time as a function of light path length. As shown in figure, we can observe that the VM medium flavor has a modest increment as the light path changes. This is due to the additional time required to transfer the larger disk size. On the contrary, the container migration time has a negligible impact on the light path change. Note that the obtained delay includes also switchponder and transponder pairs used in the management and tenant network. This paper discussed an experimental evaluation of NFV-enabled mobile networking by using OpenROADM compliant SDN-enabled network. The Consider Pronet orchestrator provides a single point of control for backhaul optical layer, Ethernet layer, and compute resources. The considered link restoration based on the backhaul capacity demand supports an optimal migration approach. The paper experimentally evaluated live migration of core network components such as HSS, MME, and SP gateway. Moreover, the experimental results show that migration is possible without UE disruption. Thank you all for your attention.